Hello, my dear trainee pilots. I'm sure you must be studying well for your CPL, ATPL, or airline exams. And I can hope that my videos are of some help to you. And like you, I'm also waiting to see you here soon. We are now doing a series of navigation numericals. And today's topic is radar, radio detection and ranging. Detect means find out where is it and the distance. And for maximum benefit, watch all my videos till the end. This is lesson 33. There are 32 videos before this. And I'm sure they will be of benefit to you. Go through them. And look forward to see you here soon. And here we go with the today's lesson on radar numericals. Here is the basic concept of a radar. Unlike in a radio transmitter, which remains on continuously till you switch it off, and transmits either a omnidirectional signal, that means transmitted in all directions, or it may be a directional signal transmitted in a particular direction. What is the difference? A omnidirectional signal will travel in all directions. Let's say this is the transmitter. The signal travels in all directions, whereas a directional signal travels in the direction of transmission. Both these types of signals are being used. Today we are talking about the radar. In the radar, the principle is that you transmit a radio signal and then wait for its reply before you send out the next signal. And this one burst or a magazine containing a number of bullets is fired all together, called a pulse. And the duration for which it is transmitted in microseconds is called pulse width or pulse duration. Now, if it's a directional signal, it will go in one direction. If it's a omnidirectional signal, it will travel in all directions. This pulse, we will go and hit the object and it will get reflected back, and at your transmitter aerial, you can receive it back. Now, to receive back, after transmitting one pulse, you have to wait till the signal has traveled the maximum distance out and come back, and then transmit the next pulse, called the subsequent pulse. This is a silent period after your transmission is over till the time next transmission goes, and it is called pulse recurrence period or pulse recurrence interval measured in microseconds. Now, you may be tempted to send a large pulse and a large distance. Now, but the problem of a large distance radar is that then if some of the pulses get lost in space due to refraction, due to traveling, hitting the aircraft at such an angle that then they are deflected in the air, then you will not receive this pulse back. So idea is to send this one magazine full of bullets, fire a number of magazines. That means a number of pulses per second, and that is called pulse recurrence frequency or pulse recurrence rate. Number of pulses per second, which is equal to 10 to the power 6 microseconds. And pulse recurrence frequency is 10 to the power 6 divided by pulse recurrence period in microseconds, and hence is a number. So if the PRF is good, the quality of the signal will or the pickup will improve. If the PRF is very small, the quality may suffer. Right. Next slide, we will take the same subject forward. There are two types of radars, primary and secondary radar. In the primary radar, the signal is transmitted and the reflected signal is received by the same area. During this period, when the signal travels out and in to a maximum distance, the radar is switched off. Transmission is off. And this up and down period is called pulse recurring period. Higher the PRP, longer is the pickup range of the radar. So next is a secondary radar in which the pulse is transmitted on a particular frequency. The aircraft receives this pulse and sends back a reply on a different frequency. There are advantages and disadvantages of both primary and secondary radar. So the transmitter which sends out the pulse is called interrogator, and the reply is sent back by the object, and this transmitter is called transponder. In the case of the ground radar, which is surveillance radar, the ground sends the interrogation signal. In case of distance measuring equipment, the aircraft sends the interrogation signal and the ground DME equipment replies back. Well, that will be reading in theory. Now, if the object is 300 kilometers away, our PRP or waiting time should be such that the signal let it travel to 300 plus 300, 600 kilometers. In 2000, it becomes meter divided by speed of 300 meters per microsecond will give you a time of 2000 microseconds in this particular case, and that is known as PRP. And 10 to the power 6 divided by 2000 will give you the PRF of this radar 500. If you know the PRF, 10 to the power 6 divided by PRF will give you the PRP. If the question is what's the maximum range of this radar, find out the PRP. Divided by 2 is the one-way travel time into 300 meters will be your answer in meters. Divide by 1000 to get kilometers, and further, if the answer is in nautical miles, convert it. You know it. Now, too long a pulse has its disadvantages when you are picking nearby objects or objects which are in the air very close to each other. One is at so many kilometers, another one is just behind him. Range. The minimum pickup range is pulse width by 2 into 300 meters. If pulse width or duration is 100 microseconds, it occupies 100 into 300, 30,000 meters in the air, which is 30 kilometers. If an object is less than 15 kilometers, let's say 10 kilometers, your signal has gone and come back, but you are still transmitting. You are unable to receive the echo. So his now minimum pickup range in this case will be 15 kilometers. So when I want to pick up close by objects, I need not send a very large pulse because that much energy is not even required. When I'm picking up an aircraft, let's say on the final approach, then I can send a small pulse. Similarly, if distance between two aircraft in the air is less than half the pulse width, they will appear as a single object. That is called range resolution. Then there is something known as azimuth resolution. That is, there are two aircraft, not one behind the other, but they are displaced laterally. One aircraft is here and other is here. In this case, they are 4 nautical miles separated. So now these two aircraft here are being covered by the same beam. This is the directional signal, and this beam or the lobe is rotating and will appear as a single object till they reach at this place. Where? Here, now. And now they will start appearing as separate objects. Can you see? So to find out at what closest distance you will start seeing them separately, use 1 in 60 rule. This will be your closing angle, distance to go, and this is separation, lateral separation between the aircraft will be your distance off track. So he can give you the beam width of the radar, two aircraft separation. I will say at what distance onwards or less than that distance, you will see these two objects separately. Apply 1 in 60 rule. And please remember, narrow beams will have a better resolution if this beam is narrow. Yeah. Now you find these two aircraft are separated. Okay. If the beam width is very large, then these two aircraft will come within the same lobe. Next, there are occasionally questions on the DME, distance measuring equipment here. Now the aircraft transmits a signal, DME replies back, and if the reply time is less, distance is less, reply time is more, distance is more. Half of this total travel distance is one-way distance multiplied by speed. Your DME calculates the distance, and the distance which it gives you is called the slant range. Here is the aircraft. Fine. So now the problem that comes is that this distance and this ground distance is not the same. Although when you are descending here, your height is also decreasing. This is the height of the aircraft. Then the difference between your slant range and the ground distance is not much. But if you are flying at a high altitude and you are near the station, let's say this aircraft, now the difference between this will be your DME reading, your distance from the DME, and here is your distance from the ground station on the ground. So to higher the aircraft, closer the aircraft, greater is the difference or error. So the method is to find out slant range is given, to find out the ground distance. Ground distance is given, what will the DME read? It will read the slant range. We use Pythagoras theorem, a square plus b square is equal to c square. And here height should be converted into nautical miles because the distance will be in nautical miles. These are the type of questions you may expect in radio and radar. And please remember, azimuth resolution depends only on the beam width and not on the PRP, PRF or pulse width, etc. So be careful. Use only the material which is required out of the question, and rest should be ignored. Now, here are some questions for your practice. Copy them down or take a screenshot or pause, and then after you have done the questions, wait for the answers. Here are your answers. Compare it with your friends. If you got all the answers correct, pat yourself on the back. If not, ask your friend who is sitting with you, or come back in the comment section to me. I will reply back to you. Now, this is more or less the last lesson from the numerical series. I'll be doing a series on theory also later on. And I hope this series has benefited you. If something is left out, do come back to in comments and I will extend this series. Now, for the time being, happy landings, good luck, and all the best for the time being. Wait till the next lesson.